Okay then, I guess we can start. Let's let others join meanwhile. So welcome back to the final session for the course Fluid Mechanics and its application. And again, this week or in this session, we will be dealing with the integral methods in boundary layers, because in the previous session we have extensively discussed about boundary layer and the Blasius solution, and hoping that you have looked into the lectures by Professor Gupta. So I hope you will get a you have a good understanding of what boundary layer actually is and how the solutions are derived, and like how the boundary layer how the boundary layers are developed. And like we also discussed about specifically about the case of flow over flat plate, where we have some exact solutions. This is specifically the Blasius solution, and how the boundary layer varies with respect to x in, in the case in the case of flow over flat plate, and how the shear stress distribution is along the x coordinate in the for the flow over flat plate. So I guess we have discussed it thoroughly. So in today's session we will be discussing about how these integral methods are used to solve such kind of problems. Like in the previous case it was quite very simple, like we have just obtained the boundary layer, how the boundary layer thickness varies, and then the shear stress distribution. But in this case we'll also see how we can apply integral methods to find the shear stress distribution for flow over flat plate without considering the Blasius solution, right? So we'll consider the flow over flat plate itself, but we will not implement Blasius solution, but we'll rather look into some integral methods to find the profile of the find the expression for the boundary layer thickness or the shear stress distribution. So like that. Okay, then I guess we can start. So also I will also request that you can stay in the session throughout the session, because it's the last session and we will be discussing some problems. So it's my tendency that I discuss the theory a bit, then go to the problem, because going at the problem right away it's like quite arbitrary from my point of view. But still, I'll go skim past very fast through these concepts so that we can give more time on the problems. So I hope it's all right. Okay then. So let's start. So here we will be discussing the integral methods in boundary layers. Okay. And for our initial case we discussed for flow over flat plate. Okay, for the flow over flat plate we found that our governing equation was of the form specifically the x momentum equation was of the form u dou u by dou x plus v dou u by dou y is equal to nu del square u by del y square. Okay, this was the governing equation for the x momentum equation for the flow over a flat plate. Okay, it's not the flow in a boundary layer, but it's the equation for flow over a flat plate. Okay, specific case for boundary layer theory. Okay, specific case. So because in the case of flow over flat plate we have a constant free stream velocity which causes the pressure gradient term along the x direction to be 0, right? So that's why this is a specific case. So keeping that in mind, what we do is that we integrate these terms, all of these terms with respect to y from 0 to delta. Well, delta is the boundary layer thickness. Okay, so I have defined all these terms as term 1, term 2 and term 3, and we will deal with all these terms individually. Okay, so the first term can be deduced in this form. Like basically if you consider if you just modify the argument in the derivative from u to u square, so this will basically give you so this term will basically give you 2u dou u by dou x, right? This term, so multiply half with it, so we get the same term here, right? So we have modified this term. The first term will be of this form. Then for the second term we take the help of integration by parts. Okay, so if we consider v as the first term and dou u by dou y as the second term, then if we apply integration by parts, so this is what we get. Then if we know that at v at y equal to 0, v is equal to 0 because of no penetration boundary condition, and u equal to 0, u at y equal to 0 is 0 because of no slip boundary condition. Okay, so applying those conditions here, so we get this to be of the form v infinity and u infinity. See here, you may know that we have discussed in the case of boundary layer theory that for y equal to delta, u is equal to 0.99 u infinity. Okay, so this was the assertion that we made while discussing the boundary layer theory, right? But just for a case of simplicity, or like for the ease of derivation, because right now here also we are discussing approximate solutions of approximate solution of Navier-Stokes equation, right? So these are not the exact solution, but we are considering approximate solutions. So keeping that idea in mind, for a case of simplicity, what we can assume is that for the ease of derivations, so we can assume that for y equal to delta, u is equal to u infinity. So in this 0.01 difference won't make a lot of variation in the solution. So keeping that idea in mind, so we impose this condition that at y equal to delta, u is equal to u infinity. Okay, and also similarly v would be equal to v infinity, even if it is very small, but we have a y component of velocity, so that's why this will exist. Okay, so keeping that in mind, and the second term this term, the second term of the integration by parts, specifically this term is dou v by dou y, u dou u by u dy. Then again dou v by dou y can be substituted by can be replaced by minus dou u by dou x from the continuity equation, because dou u by dou x plus dou v by dou y is equal to 0. That's why dou v by dou y would be equal to minus dou u by dou x. So we just substitute this in this equation to get the second term as this, okay, of this form. So if you see that this term is exactly same as the first term that we chose here, right? If you go back, the first term that we chose here. Okay, so keeping that in mind, then the LHS of the first equation, let me reduce the size a bit. The LHS of the first equation will be of this form, that v infinity into infinity plus 2 into term 1, okay, 2 times the term 1, okay. So specifically this term, okay. So again, since one more student has joined, so I will request that the student to stay in the lecture, because this is a final session. So and it's a very, I will not say it's extremely hard or difficult, but it's an important part. So I hope you stay throughout the session, because we will be discussing briefly again, like soon, discussing some problems regarding the integral methods in boundary layers. So I hope you stay, and hope this theory that I am discussing a bit, that it will help you to understand the solution, how the solutions are obtained. Okay, so stay throughout the session as long as you can. Okay, just don't leave it randomly. So that's quite true. Okay, so again in this expression, again we don't know, we know u infinity because u infinity is known before we start solving the solution, right? Because u infinity are known terms, like we know the value of the u infinity in the case of flow of flat bed. Okay, these are predefined before solving the solution. Then so the only unknown term is unknown term here in the first term is v infinity. So we need to find v infinity, and we can do it applying the continuity equation. Okay, so once we do that, so from the continuity equation, again we apply the same method that we have used, the same integration method that we used for the x momentum equation. We integrate the equation with respect to y from 0 to delta. So to get that, this term would be of this form, and this term dou v by dou y dy would be equal to dv. So it will basically give, so integration of dv would be v varying from, let me just write it, okay, v varying from delta to 0. So v at v at y equal to delta minus v at y equal to 0. So this would be equal to v infinity minus 0. So this term, that is exactly what I have written here. Okay, so from this we get that v infinity is equal to minus delta minus dou v by dou x dy integrated from 0 to delta. Okay, so if we substitute now equation 3 in equation 2, I guess I'll go a bit fast so that we can cover most of the parts, and I'll share you this note so that you can revisit. You just see the steps. If you have any doubt in the steps, you can just stop me and ask, okay, or write in the chat also, no issues. So if we substitute equation 3 in equation 2, we get this form of the equation. Okay, so now equation 2, if we go back, yeah. So now see, what we want to do is, now we want to convert these partial derivatives, right, these partial derivatives to complete derivatives, and to do that the one of the most famous methods to do this is using the Leibniz rule. Okay, so this is the Leibniz rule I have written here, so you can refer it once I share the notes, which will I share today itself. So you can see the this note. So I've just written a formula. Okay, so if we apply Leibniz rule to both of these terms, the final simplified version of the term is this. Okay, so it is simplified to this form. Okay, I will not go back deeply. So because see why this integration is difficult, because see this term, this upper limit is not a constant. Okay, it's a function of x, right? Delta varies with respect to x. If you recall it from the boundary layer theory, right? Delta, that boundary layer thickness varies with the x coordinate, right? So that's why this is not a constant. Upper limit is not a constant, but it's rather a variable which varies with x. Okay, so to keeping that idea in mind, we need to apply the Leibniz theorem so that we can convert these partial derivatives to complete derivatives. Okay, and why we want to deal with complete derivatives? It's very simple. Which will basically render the equation to convert into ODEs, which are much simpler to solve compared to PDEs, right? It's a basic fundamental mathematics, right? So that's why, keeping that in mind, we want to deal with ODEs. That is for our favor. We want to solve the equation, which will be much simpler to solve, right? So keeping that idea in mind, we convert these ODEs into PDEs into these partial derivatives into complete derivatives using the Leibniz rule to get this form. Okay. So now see, remember that this equation is actually the LHS of the first equation, the LHS of the x momentum equation. Okay. So now we are still left with a term 3, which is the right hand side of the x momentum equation. So keeping that by solving that, we get that the third term, that is basically the right hand side of the x momentum equation, is reduced to this form. Okay. Why? Because see, the upper limit for the upper limit, u is equal to u infinity and at y equal to delta, and du infinity by dy is equal to 0 at y equal to delta. Okay, this is again an approximation that the velocity approaches the free stream when the when the y coordinate is equal to the boundary layer thickness, right? So at that point, the gradient, the velocity gradient at that point will be very less, or can be approximated to be equal to 0. Okay, so now if we combine all these terms, specifically equation 5 and equation 6, we get the final form of the equation as d by dx integrated from 0 d by dx integration of u into u infinity minus u square dy integrated from 0 to delta would be equal to nu dou u by dou y at y equal to 0. Okay, and this equation is very famous. It's also known as the von Karman momentum integral equation. Okay. Kalanthi, am I going a bit fast, or is it fine? You can just write yes or no, or you can just say yes or no by unmuting yourself. That's fine. Okay, then I feel it's fine. So then also I would like to slow down a bit so that it's clear even if when you access the recordings. So okay. So now in this equation, what we will do is, we will now simplify this term again. Okay, you will see why. We know that from Newton's law of viscosity, the shear stress at the wall is equal to mu dou u by dou y at y equal to 0, right? So now if we reorganize this term, we can write this equation as this. Okay, in this form. And now see, this equation is again interesting. Why? Because if we know the velocity profile, okay, specifically these two terms, that is, if you know u, then you can just integrate this equation, take the derivative with respect to x, then multiply with rho u infinity square to get the shear stress distribution. See, it's so elegant, I must say. It's so elegant, right? For the Blasius solution, like actually while discussing the Blasius solution in the previous session, we didn't see how the third order ODE, that was f triple dash plus half f double dash, that equation, like how that was solved, right? And the solution of that equation is, if you start from the scratch, it's very difficult, right? It's very difficult. It's not that easy to solve it, and usually these are solved using some numerical methods. Okay, so keeping that idea in mind, but nevertheless those solutions are very accurate, and those are considered to be the standard results in the case of boundary layer theory. Okay, but still, now if we are okay with some inaccuracy in the solution, and we are okay with that would result in the simplification of the math involved for deriving the solutions, then it's good, right? It's absolutely fine if we look in that way as engineers, right? So keeping that idea in mind, this theory was devised, that the momentum integral solutions, right? This theory was devised that if we assume a form of the velocity profile, right? If we assume some form of the velocity profile which is usually cubic or parabolic, and its the standard is cubic, so that we get some accurate results. So if we assume a cubic velocity profile, impose the correct or appropriate boundary conditions, then we get the form of the velocity profile, right? We get the form of the velocity profile now. And if we substitute the form of the velocity profile in this equation, then we can easily get the shear stress distribution, right? That is what actually needed to calculate the drag force that acts on the surface of the body, or the flat plate in this case, right? So again, this method is quite elegant when if you see in that way, right? So okay, now we do the same thing. We substitute a certain, like if we look into, we can start by substituting a certain form of the velocity profile which can be considered to be of this form, right? Which is a cubic velocity profile, right? And see, since there are 4 unknowns, we would require 4 boundary conditions to solve it. Okay, so what we do is we impose these 4 boundary conditions. Okay, at y equal to 0, e equal to 0. It's quite obvious. Why? Because there are no slip boundary condition, right? Again, at y equal to delta, that is at the y equal to delta, that is at the boundary thickness, u would be equal to u infinity, right? As I already told, instead of considering it as 0.99 of u infinity, we consider it to be u infinity, just for simplification, right? Again, dou u by dou y at y equal to delta is 0. Why? Again, I told that the velocity gradients at the boundary thickness would be 0, because, right, the variation of the velocity is very less compared to the wall. Okay, compared to the wall, the variation in the velocity is quite less at the point y equal to delta. Okay, and finally we again impose this condition that dou square u by dou y square is equal to 0 at y equal to 0. Okay, again, okay, so we can also consider it dou square u by dou y square at 0 is equal to y equal to delta. Okay, it's quite fine, because dou u by dou y at y equal to delta is 0, then we can always consider it dou square u by dou y square is equal to 0 at y equal to delta. Okay, but still, this, as it's mentioned here, it's better to have one more boundary conditions at the wall. Okay, and it can also be devised mathematically from the governing equations. Like if we consider the equation for floor of flat plate, okay, this equation, then u is at the wall, u would be 0 because of no slip condition, right? V would be 0 because of the no penetration condition, right? This term is already 0 in the case of floor of flat plate, because the free stream velocity is constant, then the pressure gradient along the x direction would be 0, right? Then finally we are left with this term at the wall, so this would give that dou square u by dou y square at the wall is equal to 0, which is this boundary condition, right? So now it is seen that I have not solved this equation. This equation I have not solved. So if we impose these boundary conditions and solve the equation and find the value of the constants, you will find that the form of the velocity profile that we get is this. Okay, u by u infinity is equal to 3 by 2 y by delta minus 1 by 2 y by delta cube. Okay, this is again a cubic velocity profile, right? So what we do is now that to get the shear stress distribution and consequently the drag force, we substitute this form of velocity profile in this equation. Okay, so kindly wait. See, in order to save time, I won't go and derive each and every step of the solution. For that, you can pick any standard fluid mechanics book or watch the lecture by Professor Gupta. But I will, for my job is to tell you the solution methodology, like how to approach the questions and how to solve the problems, right? So that I will do thoroughly, and if you any doubt in the methodology, you can ask. Okay, so what we have done is that we have substituted this form of velocity profile in this equation, okay, the von Karman momentum integral equation, right, that we derived just a few minutes before, okay. So substitute this form of the velocity profile in this equation, so we get this equation, okay. Now what we do is, a clever transformation of variable transformation, okay. So what we do is, let us substitute eta is equal to y by delta. Again, it's completely fine if you go in and solve this equation and do this integration, okay. But again, just for the sake of the tidiness or handleability of this integration, like we can substitute this y by delta term by eta, and consequently dy would be converted into delta d eta, okay. Again, keep in mind delta is not a constant, okay, it's a function of x, okay. So keeping that idea in mind, we substitute this equation with the transformed variable to get this equation, okay. So now here again, but in this equation C, since delta is not a function of eta, here our eta is a function, eta is y by delta. So here, since delta is a function of x, we can take out delta from this integration, okay, and do this integration in terms of eta, okay. And so if we say that this integration from 0 to delta with this term is given by I, and whose value is equal to some k, okay, you need to evaluate this integration. I won't do that, okay. So I will do that for, I guess, for one example in this session, but not this one, okay. So if you do that, say this value of this integration I is equal to k, okay, some numerical value, okay, k, then we are left with tau wall by rho u infinity square is equal to k d delta by dx, okay, d delta by dx. So this is the reduced form of the this equation after we have done the integration, okay, and the variable transformation, okay. It's not necessary, you can keep it as it is, but just for the ease of calculations we do that, okay. It's a standard way. So then what we get is, now we need to know tau wall, okay, and tau wall can again be evaluated as mu dou u by dou y at y equal to 0, right. So from that we get that, since we know the form of the velocity profile, that is basically given by it was u by u infinity is 3 by 2 y by delta minus y by delta cube. If I am not wrong, I guess there is 1 by 2 factor. Yes, there is 1 by 2 here, okay. Let me just write it. U by u infinity is equal to 3 by 2 y by delta minus 1 by 2 y by delta cube, okay. Hope I am not wrong. Yes, okay. Sorry, yeah. So since we know the velocity profile, we can find this derivative, and from that we get that dou u by dou y at y equal to 0 is 3u infinity by 2 into delta, okay. Then you substitute this value in this expression, basically this expression, to get that mu into 3u infinity by 2 delta divided by rho u infinity square is equal to k d delta by dx, okay. So from that you will get an expression for delta in terms of the independent variables, okay. So because still we have not evaluated the expression for delta also, right, the boundary thickness. So from that we get that delta square by 2, like we get this expression. So if we integrate it once, we get that delta square by 2 is equal to 3 by 2k into mu x by rho by u infinity plus c, and this constant can be evaluated by imposing this boundary condition again, okay. See, at x equal to 0, delta is equal to 0. Why? Because we saw that for a floor and flat plate, the form of the boundary layer is of this form. So the boundary thickness at x equal to 0 is 0, right? Or you can say at x tends to 0, the boundary thickness tends to 0, okay. So keeping that idea in mind, we get c equal to 0, okay. So finally we get delta square is equal to 3 by k nu x by u infinity. So if we just again modify this equation a bit, we get that delta by x whole square is equal to 3 by k nu by u infinity. Okay, so again if we take the square root of this term, then just modify these terms a bit. So okay, so I guess there is some one term missing here. So if I just, there is some x missing here, I guess. So okay, yes, now it's fine. So we just take the square root of this term to get that square root of 3 delta by x is equal to square root of 3 by k into the square root of local Reynolds number to the power minus 1 by half. Okay, minus half. Okay, and see, like after we have evaluated the integration, that is specifically let me go back, this integration, if we evaluate it and get the value of k, from that we get that if we plug in the value of k in this expression root 3 by k, we get that delta by x is equal to 4.64 into rex to the power minus half. Okay, and see, this solution is quite close to what we have obtained from a Blasey solution, right? It's actually not 5 in this 5 is also quite accurate, but in the case of in the exact solution what we have derived is that delta by x is equal to 4.91 into rex to the power minus 1 by 2. Okay, and see, if you compare these coefficients, it's quite close. Okay, see the thing, like for this one we had to use solve the Blasey's equation, the third order ODE, third order non-linear ODE, apply some certain numerical methods, then we got this coefficient. Okay, but see here, just by assuming certain velocity profile, imposing the appropriate boundary conditions, and doing the integration, which is the most challenging part in this form, and thus the name integral methods in boundary layers. So the integration part is the most difficult one. So once we do that, we get the coefficient as 4.64, and if you look at it, it's quite close to what we have got from the Blasey solution. So this exactly shows like how elegant this method is, right? How beautiful this method is. Just assume velocity profile, substitute in the von Karman equation, then get the expression for the boundary layer thickness as well as for the shear stress distribution. Okay, so if we go back, we saw that the shear stress distribution was given by 3 mu infinity by 2 delta, because we couldn't solve this because we didn't know the expression for delta. So just substitute the expression for delta in this equation to get that tau r is equal to 3 mu u infinity divided by 2 root 3 by k again square root of nu x by u infinity. Okay, I have not substituted this value as 4.64. So if we go on to if we go on to again evaluate the skin friction coefficient, which is given by tau r by half rho infinity square. So so just again substitute the value of tau r in this expression to get that. If we substitute that, we will get that Cfx would be equal to 0.646 into Rex to the power minus half. Okay, and if we compare to the Blasey solution, which is we got that Cfx equal to 0.664. See, such a small variation in the results, right? Methods are a bit different because there we have used the similarity solution. Here we have used the integral methods, but still the solution that we get is quite accurate. And why we have got this? Because for our solution in this case we have used the third order or a cubic velocity profile. Okay, and if we go on increasing the degree of this velocity profile, you will get more accurate solution. But again, this again comes with more complications. Why? Because if we increase the number of if we increase the order of the or the degree of the velocity of a velocity profile, then if you go from cubic or the fourth order or fifth order, what happens here? You need to impose again some appropriate boundary conditions, right? And you need to find the boundary conditions. And as we go into higher orders, we see that the physical significance or the physical implications of the boundary conditions becomes quite irrelevant. Okay, and that's why, and it's also observed that beyond certain orders, like I guess the standard is third order, but beyond third order, it's seen that there is not much variation in the results obtained from the integral methods. Okay, so third order is, I guess, the most standard one that is being followed in the integral methods. Okay, so by default, if you're solving an equation, unless and until told, and if they're expecting accurate results, highly accurate results, the default answer should be a third order or third degree or a cubic velocity profile. Okay, I'm sorry, I'm interchanging the degree and order, so I'm sorry for that. But what I'm trying to say is your default approach should be a third order velocity profile. Okay, or a cubic velocity profile. Okay, so you can go on with that and then solve the equations. Okay, so I guess I won't go back here. Like similarly, like again, I will just show you the results. Like if you again find the drag coefficient by evaluating the net drag force on a this flat plate, we got that the coefficient that we got was 1.292, and in the case of flow over from Blasted solution, we got that this coefficient was around, I guess, 1.32. Okay, if I'm not wrong, you can just cross verify. Okay, so this is the beauty or the elegance of the integral methods, and I hope it is quite clear, like how it why it is used and how it is implemented, right? Okay, so again there was some discussion regarding displacement thickness. So displacement thickness and momentum thickness, so I will briefly discuss them, tell them the expressions. Why? Because you may be asked to derive the displacement thickness given that you have got the velocity profile, right? So you can be asked for that, or even you may be asked to find the velocity profile yourself, then find the displacement thickness to increase the the difficulty of the problem. It can also be done. Okay, so who is in the session? Okay, Kalanidhi. Okay, so if I'm audible, like could you please explain, like Kalanidhi, like can you please explain, like what did you understand from the displacement thickness? Like what does it actually imply? If you saw the lectures by Professor Gupta, like, could you please tell me, like what do you mean by displacement thickness, or what does it imply? It's already being shown on the screen, but still I want to know your understanding, like what did you understand from the video lectures? Okay then, I guess I'll presume that you have understood the concepts quite well, and that's why I'll just skim very fast through it. And moreover, the lectures from Professor Gupta are quite is easily available. You can again go back to understand the concepts. So I don't think I should invest much time in explaining this concept, but still I'll just go past a bit so that the other viewers can get to know about it. Okay. So I will just go on and read the definitions. So in the case of displacement thickness, what it basically means is that it refers to the deflection of the streamlines, or the upward displacement of the streamlines that is being observed in the case of flow over a flat plate, or in boundary layer specifically, that is being done, or the deflections are being the deflection that is being observed in the case of streamlines in order to compensate the reduced flow rate that is being caused because of the viscous effects of the fluid, okay, or the formation of boundary layer. Okay, so basically what happens is that since the velocity profile, the incoming velocity profile is of this form, which is uniform, okay, and the velocity profile at the exit is of this form, so it clearly tells us that there has been some reduction in the mass flow rate. Why? Because there has been some loss in the mass flux because of the modification in the velocity profile. Okay, and in order to compensate this loss, the streamlines are deflected upwards so that the additional mass flow rate that was incoming could be compensated here, basically to conserve the mass, or basically to satisfy the mass conservation, right? Basically whatever mass flux is coming from the inlet should be what that exactly that should be what that should exit from the outlet. Okay, so what we do is, for in this case what we do is that we consider a control volume. Basically we again implement the control volume analysis, I guess, which is, you are now quite well versed with the control volume analysis, so I don't think I need to go back and repeat it. So what we do is that we consider a control volume of this form, control volume of this form, so where the upper edge is actually a streamline of the flow. Okay, it's quite convenient, as we saw that, like if we consider the upper edge of the boundary to be a streamline, what happens is that we do not need to consider or worry about a mass flux through this edge. Why? Because there is no mass flow across a streamline. Okay, this is again a very important concept from the fluid kinematics part that we have discussed, right? So keeping that idea in mind, let's not write it. So if we consider this to be our control volume, we just apply the mass conservation at the inlet and the outlet. Since there is no mass generation, so the only term that remains are the flux terms. So at the inlet we would have the net mass flux as rho u infinity delta into b, which is basically the area, right? If b is the depth towards the perpendicular depth inside, like this perpendicular depth, then the net mass flux is rho infinity into delta b. Okay, delta is the boundary thickness. Then at the exit it would be, first we consider this part. Okay, so for that part we would have rho integrated from 0 to delta u into dy into b. Okay, for this part. Then for this part, here the velocity as the free stream velocity, so we just consider the free stream velocity dy into b. Okay, and integrated from delta to delta plus delta star, where delta star indicates the displacement thickness. Okay, so doing this integration and modifying the terms, we finally get that delta star is given by 0 to delta 1 minus u by infinity delta y dy. Okay, and this is the expression for displacement thickness. It's like from the perspective of GATE or any other competitive exams, this expression is quite important. Why? Because what happens is that they will just give you several integral expressions that might be quite similar. Like they might have they may give you square term here instead of the linear term, or you may get another term here or another term here. So they will give you different expressions and tell you that which of these expressions denotes the displacement thickness. Then you need to tick the right one. And if you just recall or if you have in memory that this term, like only the term having only one linear velocity profile indicates the displacement thickness, then it's quite easy for you, right? Just recall the expression for displacement thickness or form the displacement thickness and just tick the right answer, right? It's a like if you just recall the expression, it's quite easy for you to get the right answer in those competitive exams, right? We will see like why it's important while we discuss the momentum thickness. Okay, so again there is another analogy for displacement thickness, so I won't go and explain that. So, okay, you just can visit the lectures or just go through the notes, it will be quite clear. Okay, then again similar to that we will look into momentum thickness. So for that we consider the same control volume and same geometry. So for that again instead of mass flux we now equate the momentum flux across the two faces, right? The inlet and the outlet. Okay, so the momentum transfer at A, or basically the momentum flux at A, would be given by rho u infinity delta into u infinity. Okay, basically you can consider the inlet to be here. Okay, it's quite confusing if you consider here, it's actually here. Okay, then similarly at B, for the first part from B to delta, from 0 to delta, basically this one, so this term, so it can be written as rho into integration 0 to delta u square dy, and for the second part, this one, it can be considered as rho u infinity square delta star. Okay, quite simple and quite similar to what we have derived for the displacement thickness. Okay, and again we consider the upper edge as a streamline, so that there is no momentum flux across the upper edge. Okay, then again if we just substitute or simplify these terms, you can go back and check the derivations. The final expression that we get is that for momentum thickness we get that theta. Here I have used theta in my case. In Professor Gupta's lecture, I guess he has used delta 2. Okay, delta 1 from displacement thickness, delta 2 for momentum thickness. So don't get confused. Okay, it's just a matter of notations. Okay, for my ease, I use the notation theta. Okay, it's not different. It's exactly the same thing. Okay. So the momentum thickness theta can be given by integration 0 to delta u by u infinity multiplied by 1 minus u by infinity integrated over y. Okay, see, that's the funny part I was discussing just a few minutes before. Like here the displacement thickness is now how it is different from the momentum thickness. We just omit this term. If you just omit this term, this is the displacement thickness. Okay, so there might be instances like if you don't recall the expression, you may mix up the momentum thickness or displacement thickness. Okay, same goes for energy thickness also. So if you just recall the concept or have an understanding of what the exact expression is, or at least know the form of the expression, you can easily get the right answer. Like not only in the case of objective type questions, like even in subjective type questions, like if you are asked to derive the momentum thickness, like if you don't recall the expression, you may derive the right velocity profile or right answer and end up calculating the displacement thickness instead of momentum thickness. Okay, it might also happen. So that's why, just so that you can recapitulate and hopefully retain these expressions throughout your life. Hopefully, I have again discussed briefly about the momentum thickness and the displacement thickness. Okay. So again, momentum thickness physically indicates the deficit in the rate of momentum transfer across the 2 points because of the development of the boundary layer. Okay. Similar, since I'll just go back. Since the velocity profile at this is uniform, which contains some certain momentum flux. Okay, but again at the exit, the velocity profile you can see is of this one, which clearly indicates some reduction in the net mass flux and consequently the net momentum flux. Okay, because both are dependent on u. And since there is a deficit of momentum at the exit, if we consider the same height delta, we need to consider an extra length delta star, that is displacement thickness, to compensate this loss in the mass flux and consequently the momentum flux. Okay, and in order to do that, we define both the displacement thickness and the momentum thickness. Okay, so I hope it was clear. And again, this basic expression, this shape definition, this is shape factor, which is defined by the ratio of displacement thickness and the momentum thickness. Okay, and this again one concept, like why it is called shape factor, because specifically because it depends only on the shape of the velocity profile. Okay, so just for memory, but still. Okay, let's now solve this problem. Okay, this is again a bit interesting one. We are dealing with turbulent flows in this case, so let's just look into this problem. Okay, sorry, yeah, I hope it's visible. So consider a turbulent boundary layer over a flat plate for which the velocity profile is given by u by u infinity is equal to y by delta to the power 1 by 7. This result, the 1 by 7th law, I guess you observed in the case of flow through pipes, like turbulent flow through pipes, where the velocity profile was again given by 1 by 7th law. So I guess, as discussed by Professor Gupta, he told in his lectures that, obviously cited the work of some researchers, that he told that this 1 by 7th law is quite relevant in the case of flow or flat plate also. Like students may think that this is an expression for velocity profile in the case of flow through pipes, but still this 1 by 7th law is quite relevant in the case of flow over a flat plate also. Okay, this is basically turbulent boundary layers for flow over a flat plate. Okay, so that's why I just wanted to mention it's quite relevant here also, 1 by 7th law. Okay, so first is, now determine the coefficient of friction and the drag coefficient if the entire boundary layer is turbulent. Okay, this is the first point. We consider that the throughout the flat plate the boundary layer is turbulent. Okay, okay. Secondly, CD again we need to evaluate the drag coefficient and the skin friction coefficient if the boundary layer undergoes a transition at a critical Reynolds number given by 5 into 10 to the power 5. Okay, this is the standard value for flow over flat plate. Okay, there might be sometimes maybe 3. Okay, it's fine, but it is usually the order of 10 to the power 5. Okay, and it's given that the shear stress distribution the shear stress distribution is given by this expression. Okay, 0.225 into nu by u infinity into delta 1 by 4. Okay, and again for laminar boundary layers the drag coefficient is given by this expression. Okay, basically obtained from the Blasius solution. Okay. So if you recall now, since we know the form of the velocity profile, so what do we need here is we need the expression for delta, right? Since we are already given the expression for shear stress, we need to evaluate delta here, right? So that we can evaluate the shear stress and consequently the skin friction coefficient and the drag coefficient, right? So this is the algorithm that we need to follow, right? First we need to evaluate delta. How we will get that? From the integral solution. Once we do that, substitute it in the shear stress term to get the expression for the shear stress. Then substitute the shear stress in the expression that CD is equal to CF is equal to tau wall by half rho infinity square. Substitute tau wall here, expression for tau wall here, then get the skin friction coefficient. Okay, so this is the way to do it. Since we are given the velocity profile, we again apply the integral methods for boundary layer, and we apply the von Karman momentum integral solution, which tells us that tau wall by infinity square is equal to this. Okay, this expression. Substitute the value of y by delta u by infinity, which is given by y by delta to the power 1 by 7. Substitute this, then this integration is quite simple, just integration of two terms. But just to recall that delta is not a constant, so it will remain within the derivative. Okay, delta cannot come out. Okay, it will remain within derivative. Okay, so keeping that in mind, we get that this integration gives that tau wall by infinity square would be equal to 7 by 72 d delta by dx. Okay, see, it's not difficult. Okay, just simple integration. Do that and you get this expression. Okay, you can just cross check the integration also once you get the notes, so that you can check whether there is mistake or not. Okay, so then again we are given the expression for tau wall. Okay, so from there we get that 0.0225 mu by u infinity delta to the 1 by 4 is equal to 7 by 72 d delta by dx. Okay, so from that we just substitute, we just transfer delta in the right hand side to get an expression for an explicit equation for delta. Okay, so from that we get that this expression basically, right? We get this expression is transferred delta from the right hand side to right hand side. So once we do that, we finally get that delta to the power 5 by 4 7 by 90 into 7 by 90 is equal to this. Okay, so again after there is just certain modification to the terms. It's difficult to read out step by step. You can see the steps once you get the notes. So once we do that, finally what we get is that delta by x would be equal to 0.371 r raised to the power minus 1 by 5. Okay, see, I will tell you one trick. Okay, the trick is that after you get this expression, what you need to evaluate is not delta explicitly, but actually delta by x. Okay, delta by x, and just for your memory, I will say that this delta by x for boundary layer always varies as a function of x, rex, okay, and to the power some value, okay, to the power some value n, okay, some to the power some number n, okay. So what you need to do is that you need to deduce this expression, this complicated expression in this form, okay. So in order to do that, you may have to apply some this x to the numerator or denominator of the expression, so that you can get this expression, okay. Once you can isolate the Reynolds number, which will be a function of x, and this expression, then it's just a matter of determining the coefficient, the constant term, okay. And once you do that, you can express the equation, express a result, sorry, express your result as delta by x, which scales as Reynolds number to the power, to some power and some certain coefficient, okay, which is exactly what you need to find, okay. I hope I am clear. Currently, since you are not speaking, I am hoping that I am clear, okay. So if we do that, finally we get that delta by x is equal to 0.371, sorry, 0.371 raised to the power minus 1 by 5, okay. This is for laminar boundary layer, okay, sorry, turbulent boundary layer, that's why this coefficient is not matching, okay. So don't get confused. And also, the more important, the power of the Reynolds number is not matching, okay. So once you do that, just substitute the expression for delta in this, as I told you, tau 1 can be evaluated as, tau 1 will be equal to, sorry, CF could be evaluated as tau 1 by half rho infinity square. So just substitute this expression for tau 1 here, then you can easily get CF, which will be function of x, so it is given by this, and consequently you can find the expression for drag force also, okay. So now the second part of the question is this one, okay. So here what we are told is that in the previous case we have assumed that the boundary layer is turbulent throughout the flat plate, okay. Just wait for 1 minute, okay. Okay. So in the first part, we have assumed that the boundary layer that exists over the flat plate is turbulent throughout the boundary layer, okay, throughout the length of the plate. But in the second part, they have mentioned that there is a point of transition in the flat plate, which means that before the point of transition the boundary layer is laminar, and after the point of transition the boundary layer is turbulent, okay. So you need to evaluate both these parts, the turbulent part as well as the laminar part. What would be the difference? The difference is that for the case of turbulent boundary layer, we have to substitute the results from our integral solutions that we obtained by considering the given velocity profile. We need to substitute those values in the case of turbulent boundary layers, and for the laminar boundary layers we can just substitute the standard results that we got from the Blasius solution, okay, as it is given in the question, okay. So again I won't go on to solve the entire solution, but I'll just give an idea, okay. So from this expression, okay, REXCR is equal to U infinity XCR by nu. So since these three terms are known, you can evaluate the critical critical point, okay, or not the critical, yes, where the point where the flow transitions to turbulent, okay. So once you evaluate XCR, why it is important you will see. So first step is to evaluate this XCR, okay. I am not using the term critical point because sometimes you may get confused with the concept of critical point in the case of thermodynamics, okay, and the liquid vapor domes, okay, there's also critical point. So not to get confused, I will just mention it as XCR or X critical, okay. It will be quite convenient, not confusing, okay. So then this expression is that is important, okay. This expression is important. So what we consider is that from 0 to XCR or X critical, the flow is laminar. Okay. And then from X critical to L, X equal to L, let me just write it so that it's not confusing. Okay. X equal to 0, X equal to XCR, and X equal to L. Okay. So from 0 to XCR, the flow is laminar. So in this region, you can apply all the Blasius solution in this region. Okay. And from XCR to L, the flow is turbulent. So you need to apply the von Karman solutions. Okay. Because Blasius didn't give us the solution for turbulent boundary layers. Okay. That's why in that case we apply the von Karman solutions. Okay. Because it never mentioned that whether it is valid for whether it is valid for laminar or turbulent boundary layers. Okay. It's just told that like until the boundary layer theory is valid, up to the point that the boundary layer theory is valid, the solution will be valid, right? So like, when does the boundary layer theory becomes invalid? Like we saw that at the point of separation, the flow separates, the boundary layer theory becomes invalid, right? So just before the point of separation, this von Karman solution would be valid. Okay, be it laminar boundary layer or turbulent boundary layer, it doesn't matter. Okay, but in the case of Blasius, it was explicitly mentioned that the flow, that the boundary layer is laminar. Okay. So this part, evaluation of this part is quite easy. How? Because if we if we see that the drag force from 0 to XCR can be evaluated directly, right? So this length we know, this length is XCR, right? So 0 to XCR, the length will be XCR. So once we know that length, just substitute the value of XCR in this expression, which is given by CD into half rho infinity square B into XR. Okay, where CD is the drag coefficient for laminar flow, which again has an expression which is given by 1.328 Rex to the power minus half, right? So here Rex to be substituted by REXCR. So X is substituted by XCR. Okay. So this is clear. So this is easy to evaluate. Now this part is difficult. Okay. So see, the boundary layer theory like doesn't specifically tell us like how to evaluate the drag force if you are starting from an arbitrary point of the flat plate. Okay. So by default, it assumes that the initial point that we choose for determining the drag forces or the shear stresses are from the leading edge. Okay, the calculation is taken from the leading edge of the flat plate. Okay, so in order to compensate that issue or compensate this problem, what we do is that first we evaluate the the drag force that could have been because of the turbulent boundary layer from the leading edge to x equal to L. Okay, which is exactly be done here. Okay, so what we assume is that there must be a turbulent boundary layer from the leading edge to x equal to L. Okay, because for that we have an expression. Okay, which is given by this. Okay, so we evaluate the drag force, the turbulent drag force from x equal to 0 to x equal to L. Okay, but what we actually need is that the drag force that exists for turbulent boundary layer from x equal to XCR to x equal to L. Okay, and in order to do that, what we have to do, we have to subtract this part, right? We need to subtract this part, right? This part we don't want, right? So in order to do that, what we do is that since we have assumed that, like, please focus or give attention to this part. Okay, this is very important. This is very important concept. Okay, so first what we do is that since the evaluation of these drag forces are always assumed to be started by default from the leading edge, so we cannot just evaluate the drag force from some certain arbitrary length over a flat plate. Okay, the length must be started from the leading edge. Okay, and since there is this issue or what to say, I'm not getting the correct one. Like basically, it's some issue or problem with this concept or theory. So we need to overcome that, and how we overcome that is what I'm going to discuss. So in order to do that, what we assume is that since the boundary is turbulent, so what we assume is that we assume boundary to be turbulent at a drag force, considering that the flow is turbulent throughout the boundary layer. Okay, so we start from x equal to 0 and x equal to L, is equal to L, and then evaluate the drag force. Okay, because of a turbulent velocity profile. Okay, this is what we do. This is what we have done here. Okay, the first expression. Now, secondly, since instead of a turbulent velocity profile, the velocity profile here is laminar, so what we need to do is that we need to subtract the contribution of the drag force because of a turbulent velocity profile from this part. Okay, for this part. So that is what we exactly do. We just subtract the contribution of drag force because of a turbulent velocity profile for this part, from x equal to 0 to x equals CR. That is what exactly be done, and you can also understand in that way. Then since this is removed, we just substitute it with the laminar solution. Okay, so that is what is being done here. So once we do that, we get the expression for the drag force, and since we get the expression of drag force, just divide it by this term, half rho infinity square into dl, to get the expression for the drag coefficient, which is given by this expression. Okay, so I hope this was clear, and the solution methodology, like how to evaluate the solution when there is a transition in the boundary layer. So I hope it was clear. Okay, and how both the Blasius solution and the von Karman integral solution is being applied or applicable in this solution methodology. Okay, so I hope this part was clear. Okay, then now we look into another question. So this again quite simple, so still let's just go through it. Okay, let me just wait for a few minutes. Okay, so you can go through the question meanwhile, and just see like how to solve the problem, right? See, the algorithm for solving the solutions are quite similar. Okay, you just need to know what is being given and what to evaluate. Okay, I hope you can just go through the question for a few minutes, then I'll be back. Okay. Okay then, let me just go through the question. Okay then, let's go to the question once. Air at standard conditions flow over a flat plate. Okay, so the geometry is given. The free stream speed is 3 meters per second. Find delta, this is basically the boundary layer thickness, and the shear stress at x is equal to 1. Okay, from the leading edge, see, that's what I was mentioning. This theory is an issue that all the solutions are being assumed to start from the leading edge of the flat plate or any geometry that is being given. Okay, so that's why I had such in-depth discussion of the solution methodology when we have some arbitrary starting point for our evaluation, right? So I hope it was clear. So it is told that find delta and tau 1 at x is equal to 1 from the leading edge of the flat plate, assuming a cubic velocity profile. For air, it is just the property values. The kinematic viscosity is 1.5 into 10 to the minus 5 meters square per second, and density is 1.20 kg meter cube. So from this question right itself, we can say that they are not asking us to solve or take the help of the Blasius solution, but rather consider the von Karman solution. Okay, the von Karman integral solution. Okay, so by default, if you start this solution, you had to assume a cubic velocity profile, substitute the expressions, just write the steps. Okay, start with a cubic velocity profile. So there will have 4 constants. Then apply the appropriate boundary condition. Apply appropriate. Again, this is important. Okay, there must be a physical meaning behind the boundary conditions. Okay. Then evaluate the constants. Okay, evaluate the constants. So once you do that, get the velocity profile. Once we get that, substitute in von Karman's equation. Find delta, then find tau wall, and then consequently CD and CFX. Okay, so this is the algorithm they need to follow. Okay, so this is exactly what we had to do, but since we have already solved a cubic velocity profile, as we just discussed some time before in this session itself, so actually it was way back, so that's why I am not saying few minutes, but we have discussed the solution in this lecture, in this session itself. So we got that the form of the cubic velocity profile, given that we apply the appropriate boundary conditions, is given by this expression. Okay, where eta is equal to y by delta, and we also got that the boundary thickness varies as this expression. Okay, so this is what we had to actually evaluate, but since we already got a solution, I will just substitute it in the expressions. Okay, so what we get that, so once we since we know the expression for the boundary thickness, so we have already reached here. So once it is known, we need to know the Reynolds number to calculate delta. So once we do that, we get that delta is equal to 0.0103 meter or 10.3 millimeter. Okay. So numerical values are given. This will give some numerical solutions. Okay, basically numerical values with our solutions. Okay, it will not be some functions. So now we need to evaluate shear stress, right, at the wall. So in order to do that, again just substitute the value of the velocity profile in this expression. So evaluate this derivative. Then substitute the value of delta. Okay, so once you do that, we get that tau r is equal to 3 mu u infinity divided by 2 into delta. So 3 is constant, mu is known, u infinity is known, and delta is just we evaluated again. Okay, so once you do that, we get the expression for tau r. Okay, this is given by 8.06 into 10 to the minus 3 Newton per meter square. Okay, again just for that, I know you will not make a mistake, but still, before submitting the final solution, just look at the units of your expressions. Okay, okay then. So we again look at the next question. Again, it's again interesting one. Okay, so air moves over a flat plate with a uniform free stream velocity of 10 meter per second. Okay, at a point 15 centimeter away from the front edge, similar name to the leading edge, like front edge, leading edge, same thing. The leading edge of the plate, what is the boundary thickness? Use a parabolic velocity profile. Again, this is exactly same. So you need to calculate the boundary thickness. So, and we have told that use a parabolic velocity profile. So it basically means is that apply the von Karman solution. Okay, von Karman solution. So to do that, again we assume a parabolic velocity profile. So this is what you can do, or just like the previous case, you can also consider it to be of this form. Okay, it's the same thing. Like after you, like it's not the same, but whether you choose this form or this form, after you apply the boundary condition, you will end up with the same expression, okay, the same expression for the velocity profile. So once you do that, we get that, and these are the boundary conditions, okay, and these are quite obvious ones. This is at y equal to 0, u equal to 0 from no slip boundary condition, at y equal to delta, u equal to u infinity, because this is what the definition of boundary thickness is, and finally at y equal to delta, the velocity gradients are 0, okay, quite obvious and quite intuitive, right? No need of explanation, I guess. So once you impose these boundary conditions to any of this velocity profile, you get that u by infinity is equal to 2 into y by delta minus y by delta whole square, or 2 eta minus eta square, if eta is equal to y by delta. So once you do that, since the form of the velocity profile is known, you can easily evaluate the substitute this in the von Karman's equation. So from that, so before that we just express tau in terms of delta, so that we can get an explicit expression for delta, okay. So if we know the form of the velocity profile, we just substitute in this expression for tau 1 to get that tau 1 is equal to 3 mu u infinity by delta, okay. So after that, so you may ask that, sir, since we know tau 1, we can evaluate tau 1 here itself, right? But see, the issue is that we don't know delta, right? So in order to tau 1, we anyway have to evaluate delta first, okay. So that is the catch, and that's why I need to apply the von Karman's solution, right? So once we know that, just substitute these two in the von Karman's expression to get that 2 mu u infinity by delta is equal to rho u infinity square d delta by dx, integration from 0 to 1, 2 into eta minus eta square, 1 minus 2 eta minus eta square, okay, into dn. And this one is obviously come because of a variable transformation, and instead of integrating raised to y, we are integrating for eta, where the value of eta changes from 0 to 1. Okay, how? I will just show it. Like instead of y by delta, we are solving for eta, right? So here again, then dy would be equal to delta d eta. So as y tends to 0, eta tends to 0, so the lower limit remains the same, and if as y tends to delta, eta would tend to 1. Okay, this is what exactly being done here. Okay, definite integral, the concept of definite integral. Okay, just recall that and apply it. Okay. So once you do that, we get once we evaluate this integration, we get that 2 mu by delta rho u infinity is equal to 2 by 15 into d delta by dx, or d delta d into d delta is equal to 15 mu by rho infinity into dx. Again, just integrate it and evaluate the constant, which turns out to be 0 after applying this condition. Okay, so we get that delta square by 2 is equal to 15 mu x by rho into u infinity. So delta would be square root of 30 mu x rho into infinity. And again, as I told, it is quite convenient, or it is a good practice to express this in terms of delta by x, some function of rex to the power some value, okay, some integer, not integer, some positive number. Okay, so after we do that, we get that delta by x now is equal to 5.48 divided by rex. Okay, now see the catch. That's why I wanted to show this result. When we were dealing and the Blassius solution, if you recall, the Blassius solution was delta by x is equal to 4.91 to the power divided by rex to the power half, right? And for the cubic solution, we got that delta by x is equal to 4.64 So here now you clearly see the variation in accuracy while for choosing different degrees of polynomials, right? And now I recall degrees is the right word, okay? Degree of the velocity profile or degree of the polynomial, okay? So when we choose a cubic profile, this is for a cubic profile, cubic Blassius and this is again
parabola. So from these results you can clearly see that the variation in the value of the coefficients is larger in the case of parabolic profile compared to the Blasius one. When we compare, so a difference in the value of these coefficients when compared to the Blasius solution is larger in the case of a parabolic one when compared to the cubic solution, right? So this is what it shows, like how choosing a higher degree of the polynomial for the Blasius profile gives us more accurate results, and we'll eventually see that when we choose a linear Blasius profile, the discrepancy in the value of this coefficient is even more, right? So as engineers or mathematicians, accuracy of solution is quite important for us, right? Even though we are calculating approximate solutions, but accuracy of the solution is quite important for us. Until now we assume that the Blasius solution is the most accurate one, right? So we see that even after applying some cubic Blasius profiles or parabolic Blasius profiles, we can still approach the same solution, but we see that as the degree of the polynomial or the degree of the Blasius profiles increased, the accuracy is also increased. But again we see that if we increase it beyond some certain degree, again there is no point of increasing these degrees, because the boundary conditions or the physical relevance of boundary conditions becomes quite unclear for higher degree of polynomials. Okay, so I hope this was clear. Then again, just simply what we need to do is, since we finally got the expression for delta, evaluate the Reynolds number and just substitute the Reynolds number to get the value of delta, which is given by this expression. To get that, delta is equal to 2.59 millimeter. Okay, so this is what was exactly asked. So I hope it is clear. Again, so okay. So I guess I will skip this question. This is very easy. You can just go and just substitution of values. Okay? So I don't think I need to look over it. This okay, so this result is quite interesting. Okay, let me just go to the question. Okay, and this will be the final question for the moment integral solution, and moreover for this session or this course, this is the final question. So I hope you give some special emphasis for understanding this question, and after that we will just briefly discuss about the boundary layer separation, just a theoretical understanding, which is also important, but again this is quite properly discussed by Professor Gupta, so you can visit his lectures, but if you want I will discuss it briefly about it in this session also. Okay, but from the questions perspective, this is the last question for this session as well as the entire course. Okay then, water at 15 degrees Celsius flows over a flat plate at a speed of 1.2 meter per second. Okay, so this sentence itself given us two information. What are they? First, it is geometry. It is a flat plate, and it also tells us that the speed of the free stream is, or U infinity, is 1.2 meter per second. Okay, the plate is 0.3 meter long and 2 meter wide. Okay, these are just the dimensions. Okay? Long in the sense that it is given that this is 0.3 meter long. It tells us that the length or the leading edge starts from x equal to 0 and the trailing edge is at x equal to 0.3 meter. Okay, assume the velocity profile is approximated by linear expression for which delta by x is equal to 3.46 divided by square root of the local Reynolds number. And this is what I was telling. We have not evaluated this expression, but still see the discrepancy in the value of the constant term when compared to the Blasius solution. I will just recall it again. For the Blasius solution, it was so this is the outcome, or this is the result of choosing lower order polynomials, right? This is quite inaccurate. Even though we will get results we will get, but the accuracy of result is what is important, right? So this is the discrepancy. You can clearly see there's huge discrepancy in the value of coefficient, and it's quite not agreeable or not acceptable in the case of standard results for fluid mechanics. Okay, so this question may help you to understand the concept, but result wise this is not accurate. Okay, but still we need to evaluate the solution. We just go through the questions. Okay, determine the drag force on the flat plate, and given that these are the fluid properties. Okay, mu is equal to 1.1 into 10 to the minus 6 meter square per second, and density is 1000 kg per meter cube. Okay, so the drag force due to skin friction acting on both sides of the plate is given by Fd is equal to 2 into 012 tau wall bdx. Since it is told that boundary layer exists on each side of the plate, okay, and it is laminar. Okay, so even though it doesn't bother us whether it is laminar or not, but still they mentioned. Okay, what we can actually do is that you can since it is laminar, you can compare your results with the Blasius solution and see the discrepancy. I have not done it here, but you can do it yourself. Okay, just to see the inequality that you get for assuming linear velocity profile in the case of von Karman solution. Okay, so since the velocity profile is linear, we get that tau wall will be given by this form, this expression. Okay, and again we just since now we know the value of tau wall, just substitute this expression of tau wall in the drag force to get that. If you substitute this expression for tau wall in this expression, we get that Fd is given by, just do the calculation. Okay, I will just don't go on and tell you the entire expression. So we get that Fd is equal to 4 mu infinity b by 3.46 into the square root of Reynolds number at the trailing edge. Now you may ask, like, why we have not implemented the von Karman solution? See, it is quite obvious. Why? Because we have been explicitly given the expression for the variation of delta in the question itself. Okay, so von Karman solution is implemented to find the variation of delta, and then from that we evaluate the shear stress, right? But since delta has already been given to us, we don't need to apply the von Karman solution, right? So once we do that, we get that the shear stress is equal to, the drag force is equal to Fd is equal to this one. Then we evaluate the Reynolds number REL, which is quite simple because L is given, so it's quite simple. So we get the drag force at x is equal to L is given by 1.745 Newton. Okay, as an exercise, you can just evaluate the same thing for considering the velocity profile. Or instead of this, you consider this profile for the boundary layer thickness. Substitute this in this expression. Then calculate the drag force and just see how whether there is discrepancy in the value of the drag force. Okay, and I know there will be a very high discrepancy. Okay, you can check that. Okay, just a good exercise to get your concepts straight. Okay, so now for the final part of this session and the course also, we'll discuss briefly about flow separation, okay, or flow past immersed bodies, okay, and how the flow separation occurs in those cases, okay. And in the lectures also, I guess I would suggest that you go through the lectures, because in the lectures Professor Gupta has very beautifully explained the flow separation phenomenon with some appropriate diagrams and plots to show the variation of the velocity profile and the velocity gradients, as well as second derivative of the velocity. That's quite beautifully explained there. So I highly suggest that you go through the video lectures by Professor Gupta. But still, I will also try my best to explain the theory of this concept of flow separation. But still, let's just see. Okay. So since this is a very theoretical part or theoretical explanation towards this concept of flow separation, I will just dictate the sentences that's written here, and obviously which are quite conceptual in themselves, but and explain whatever is necessary. Okay, but if you have any doubt, then please just stop me and ask. Okay, that's what you can do. Okay. So in the case of flow past immersed bodies, which basically means that the body is completely immersed in the fluid. Okay. Just 1 second. Example would be again the flow of flat plate. Okay. So flat plate can be considered to be completely immersed in the flow, where the movement of the fluid over the flat plate exerts some force on the plate. Okay. And by the very concept, or by its very root, or I must say by its very root, the concept of fluid dynamics is that we are interested in the force that acts on the body by the virtue of the motion of the fluid over it. Okay. So this is again an application part, or you can understand it's a very application based concept of fluid mechanics. Okay. So we are interested in the forces that arise because of the fluid flow over a surface, and how these forces affects the surface that is being completely submerged or partially submerged in the fluid. Okay. So we will not go into very, very difficult geometries, but in this case we will specifically discuss about flat plate and curved surfaces. Okay. So let's just go through it. Okay. So what are the forces that are experienced by a fluid particle located within a boundary layer? Okay. So the first is the forward pull of the outer stream transmitted into the boundary layer by the viscous action or momentum transport. Okay. Since the fluid will move over the flat plate, it will try to pull the plate along with it because of the viscous effects. Okay. Consequently, the slowing down effect of the wall shear stress. Okay. So what will as a reaction to this pull, the flat plate will try to slow down the incoming flow, right, or the flow that occurs over it. Okay. And the third type of force is the force due to pressure gradient. Since there might exist some pressure gradient in the case of flow over some submerged bodies, but that we didn't discuss in the case of flow over flat plate, but it may also exist, right? So the pressure gradient will also incur some force difference that would result in some resultant force over the flat plate or the body that is being submerged in the fluid. Okay. So these are the distinct forces that acts in the case of flow over a submerged surface or submerged body. Okay. So you can consider this diagram, this curved diagram, which can be a ball or airfoil or any curved surface. Okay. And if we consider this streamline, okay, this streamline that is straight. Why? Because we consider this streamline to be quite farther away from the body. Okay. And moreover, one more thing is that the curvature of the body itself may help in inducing pressure gradients. Okay. So that's one expression. This is one conclusion. Okay. So if we consider this streamline and consider the surface of the body to be another streamline, so you can see that this resembles a very well-known geometry that we have discussed quite a while ago when we were discussing flow measuring devices. So if you recall, it resembles the venturimeter. What we saw is that as the area decreases, the velocity increases and the pressure decreases, right? Consequently, as the area increases, the velocity decreases and the pressure increases. In the case of subsonic flows, obviously we are discussing the subsonic region. Okay. So it tells us that since the area is decreasing as the flow approaches the center line, say, since the area is decreasing, the velocity will go up and the pressure will go down. Okay. So from this inlet to this point, the pressure goes on decreasing as we reach to this point. Okay. So it basically tells us that from here to here there is a favorable pressure gradient. Okay, right? And by favorable pressure gradient I mean a decreasing pressure. A decreasing pressure will induce a flow towards the positive, or I must say a decreasing pressure towards a coordinate axis, or say in the positive x direction, would induce a flow towards the positive x direction, right? Which is what we have observed in the case of flow through pipes. How a negative pressure gradient induced a flow in the positive x direction. Okay, so that is where we discussed the concept of adverse pressure gradients and favorable pressure gradients. Okay, but we didn't discuss it thoroughly. So in this case we will discuss a bit thoroughly in the case of say flow over flat plates or curved surfaces. Okay. So here, so as I told you, from here to here there is a favorable pressure gradient because the pressure goes down as we approach the center line. Okay. But again, from this point to the exit, since the area is increasing, the velocity will go down and the pressure will go up. And since pressure is increasing as we go towards the positive x direction from the center line to the exit, there is an adverse pressure gradient. Okay, and we will see how this adverse pressure gradient affects the velocity profile or the net force that acts on the body and even the boundary layer. Okay, so this is again a schematic diagram that shows the variation of u, the velocity gradient, and the second derivative of velocity with respect to y for flow over this curved surface. Okay. So for the case of dp dx less than 0, or basically favorable pressure gradient, we saw that the velocity, this adverse pressure, the favorable pressure gradient induces a flow towards the x direction. So inducing a flow basically means that the flow velocity increases as we go in the positive x direction, right? So that is what being basically shown here. So as dp by dx is greater than 0, so if dp by dx is less than 0, this is basically favorable pressure gradient, the velocity would increase as the with y. Okay, the velocity this will be the form of velocity profile. So velocity will increase as we move up towards the free stream. Okay, consequently, since u increases with y, it will basically tell us that the velocity gradient is positive at the wall. Why? See, since velocity increases, the slope velocity increases. There is a very abrupt increase in the velocity from the at the lower values or the lesser values of y, and this abrupt change in u basically reduces as we move up towards the boundary layer. So this increase or this variation in this velocity consequently decreases as we move up the boundary layer, right? So this is what being exactly shown here. So initially it is positive at the wall. At the wall, this velocity gradient has a positive value, and as we move up to the boundary layer, this velocity of the value of this gradient gradually decreases and is almost equal to 0 at y equal to delta. Okay, let me just write it. Dou u by dou y is almost equal to 0 at y equal to delta. Okay. Then consequently, you can see that from this diagram, since dou u by dou y, or the velocity gradient, is decreasing as we move up as we go up in the positive y direction, so dou square u by dou y square will be 0 at y equal to 0, right? It will be negative at y equal to 0, and consequently reach at will be equal to 0 as once one approaches y equal to delta. Okay, so I hope it is clear. Now we look into the case of a adverse pressure gradient, which is again quite interesting. Okay, so I hope you try to focus here, and I hope I'm able to explain it. Okay, it's quite intuitive, but like in the same place, quite difficult to interpret it first. Okay, so I also feel the same difficulty, but I hope I'm able to make it clear. Okay, I will try my best, and if you're still unclear, you can just go to the lecture by Professor Gupta, so that you are perfectly clear in the concept. Okay, but this is important. Okay, I hope you focus upon it a bit. Okay, so it is told that dou p by dou x is greater than 0 in the case of adverse pressure gradient. So rather than directly approaching from directly starting from this profile, we start from this one. Okay, and what will be the value of dou square u by dou y square in the case of adverse pressure gradient? How to obtain that? We can obtain it using the boundary equations. Okay, not the boundary equations for flat plate, but the general boundary equations. Okay, in that the pressure gradient will exist, right? Okay, so at the wall, if we consider the boundary equations at the wall, then u equal to 0 because of a no slip, right? Let me just, okay. So u would be equal to 0 because of a no slip. Similarly, v would be equal to 0 because of the no penetration boundary condition, okay. So what we finally get is that nu into dou square by dou y square at the wall is equal to 1 by rho dou p by dou x, sorry, dp by dx. And now if dp by dx is greater than 0, it will basically mean that dou square u by dou y square at the wall is greater than 0, okay, at the wall, not in general, okay, at the wall. We have considered this equation at the wall, okay. This, so it basically tells us that from this equation we get that dp by dx, for dp by dx greater than 0 or for adverse pressure gradients, dou square u by dou y square is at the wall is positive or greater than 0, okay. So this is what we exactly shown here, okay, it is positive. And we also know that whatever may be the pressure gradient condition, it is adverse or favorable, the second derivative as well as the first derivative approaches the value 0 as we reach the boundary thickness or y equal to delta, okay. So it will have a value of 0 at y equal to delta, okay. Now the thing is how it will reach this point. So I have drawn it here, but it is not necessary it should be like this, right? It may happen like this also, or like this also, it may happen, right? But why I have chosen this? See, the thing is that say at a point, let us just try to understand in a intuitive manner, okay, like just try to visualize it yourself, okay. Say at a point in the boundary layer or at a point in the flow field which is specifically near the boundary layer, the velocity profile approaches its maximum, okay, it approaches its maximum. So say at y equal to delta, let me just try to write it, okay, I hope it is clear. Y equal to delta, u equal to u max. So it will basically imply dou u by dou y is equal to 0. And since u is a u max, so it will basically tell us that dou square u by dou y square is equal to negative. Sorry, negative, right? Since the function u gets its maximum value at some certain point that is usually close to the boundary layer thickness, so the first derivative for the velocity gradient will be 0 at the boundary layer thickness, and dou square u by dou y square, not exactly the boundary thickness but near the boundary thickness, and dou square u by dou y square will be negative. Why? Because the function has a positive value at that particular point, okay. This the basic concept of maxima and minima. If you know, you will understand this, okay. But we also know that dou square u by dou y square has to be 0 at y equal to delta or some point in the flow field, like not exactly y equal to delta because u, sorry, I'm just writing, u is equal to u infinity at y tends to infinity, okay, and u is equal to 0.99 u infinity at y equal to delta, okay. So since we know this one, and so it means that dou square by dou y square has to be negative, and also it has to reach a value 0 once the y approaches infinity, okay, or in this case some value nearby the boundary layer thickness. So in order to incorporate this negative value of dou square by dou y square, and also the fact that dou square by dou y square is a continuous function, so the only possible way to compensate both of these facts is the fact that the velocity or the profile for the dou square by dou y square should be of this form, okay, which is shown by this figure. So I hope it was clear, okay. So again you may ask that, sir, if you are telling that y u approaches some maximum value at y equal to say delta, then why not this term being completely neglected and can just be here, right? It should approach 0 at y equal to delta. See, the thing is that it might also happen that which usually happens in the case of flow over curved surfaces, since there is an applied pressure gradient, or a pressure gradient exists over the surface, the flow would usually accelerate within the boundary layer or within a certain region. So, or wherever there is an favorable pressure gradient, so the flow would accelerate at that point, then reach a maximum value, and then consequently diminish to the free stream value. Okay, I'm sorry, I guess I am confusing you a bit, but I will show you with the help of a diagram. Okay, so what happens is that, like, say the most popular example is the case of flow and airfoil. Okay, so consider an example. So this is an airfoil, and this is the free stream velocity. So what usually happens is that the velocity profile in the case of airfoils are of this form. Okay, let me just try to draw it. So it is 0 at the surface because of no slip condition. Then it would increase to a certain value. It will reach a maxima. Okay, and then interestingly enough, and this maxima might be larger than the free stream velocity. Okay, why? Because of this curvature. This curvature results in an acceleration. This curvature results in an favorable pressure gradient, which results in an acceleration of the flow, which may cause the flow to accelerate, which may cause the flow to have a greater velocity, which may cause the flow to have a velocity greater than the free stream velocity at certain points in the flow field. Okay, this is rightly observed. This is not something that I am making up. Okay, this is rightly being observed. So the velocity profile reaches a maximum value that is usually of the order of boundary layer thickness, and then what happens is that it usually reduces to certain value and then reaches a constant value, and this constant value is the free stream velocity, and this maxima u max is usually greater than u infinity. Okay, and u max, why this is happening is it is exactly happening because of the curvature of the profile or the curvature of the body, which is inducing a favorable pressure gradient, which results in the acceleration of flow in the nearby regions or the region close to the airfoil. Okay, let me just see if there's many. Okay, there's no color. Okay, I hope you understand it. Okay, so there's one. That is what being exactly mentioned here. Okay, so okay. So this is how the velocity, the dou square by dou y square, this profile would look like in the case of flow separation. So not flow separation, adverse pressure gradients. Okay. Similarly, as I mentioned here, the velocity profile would look in of this form, that it increases up to certain point and then increases to certain value, and then again it may decrease. Okay. So it has reached a maxima at this point, and that's it has reached a maxima at this point. So if we just compare it, so it's a bit wrong. So okay, let me just tell you. Say if the velocity profile has a maxima at this point, so this negative would be at this point. Okay, so at this point, and then the velocity gradient should be 0 at that point where the velocity reaches its maximum value. Okay. So what this blue line exactly indicates is the inflection point. Okay. If you recall that the second or the first order derivative just tells us the rate of change of that certain parameter, and the second order derivative tells us the rate of change of the slope, or how the slope varies in the case of the certain parameter, or it basically tells us the point of inflection, right? So the second order derivative has a physical significance of implying the inflection point or the inflection of the particular curve or the parameter, right? So at this point where the dou square by dou y square is equal to 0, it indicates the point of inflection, right? And in that point, in that case, at the point of inflection, dou u by dou y would have the maximum value. Okay. And consequently, the curvature of the velocity profile would change at that point. Okay. So if it was like this form, then the curvature would change at this point. Basically, S-shaped curve it would signify, and at this point, the curvature of the velocity profile has changed from concave up to concave down. Okay. So I hope it was clear. So I hope I was able to clarify the concept of how the adverse pressure gradient, how the velocity profile, the pressure, the velocity gradient, and the second derivative of velocity changes with respect to y in the case of a favorable pressure gradient and an adverse pressure gradient. Okay. And again, one more thing is that the existence of the point of inflection. Okay, this is very important point. Okay, I hope you note it down. The existence of point of inflection is a hallmark of adverse pressure gradient. A flow with favorable pressure gradient will never have a point of inflection in the velocity profile. Okay, only a flow that has or that is being that has an adverse pressure gradient in it would show a point of inflection in its velocity profile. Okay, I hope you note down this fact, note down this point, because it's very important and also maybe asked in the competitive exam as 1 mark questions. Okay, so I hope you take a note of it. Then again, we just look into the concept of boundary boundary separation, and we also see that the boundary layer theory that we have discussed, both the Blas's solutions and the, or let's just leave it, the Prandtl's boundary layer theory itself. As most important thing was that these solutions are invalid beyond the point of separation. Okay, like once the flow is separated, the boundary equations are invalid. Okay, so this is very important. Okay, so here, let me just go back. So here also, once the velocity reaches its maximum value, so dou u by dou y would be 0, right? As I told you. So dou u by dou y is 0 and when velocity reaches its maximum value. Okay. So I'm not able to draw it here, but it basically means that this will be lie on the same line. Okay. So u equal to u max and dou u by dou y equal to 0, and if I just superimpose it a bit, basically means that dou square u by dou y square is equal to negative. Okay, so I hope now it is perfectly clear. Okay. Just see, I am emphasizing it so much because it's very important concept, and usually there's a lot of misunderstanding regarding these concepts. Okay, I myself have to read so many times so that I am clear, so that I hope I'm able to convey these concepts in a quite proper manner to you. Okay then. So this was again discussed in the lecture, but still I will try to tell you a bit. So we consider a curved surface. Okay, since as I told you, this curvature would induce pressure gradient, right? Because like the diagram that we shown here, consider a streamline here. So at this point, you can consider the flow to be approaching a converging part. So the flow would accelerate up to this point, and then once the flow crosses this point, the flow will try to decelerate, and then this deceleration of the flow because of the existence of an adverse pressure gradient would result in flow separation. Okay, so these are the velocity profiles at different points in the flow field. So you can see here the first two velocity profiles, the flow is accelerating and is completely attached to the flow. At the third point, the flow is still attached, but it is the onset of separation in the case of this particular shape, right? And at this point, you can see dou u by dou y at the wall is equal to 0. Okay, and this is what inherently signifies flow separation. Okay, and as we move further, it may also happen that this flow may this value dou u by dou y can in fact also take negative values as the flow is as the flow is subjected to further adverse pressure gradients. Okay, so this is what we exactly told here. Okay, and this is again an important way of understanding flow separation, that since the flow is separated, one may also consider this separated region, right? This separated region as a wall, and then consider that the flow is starting from this point. Okay, and it basically signifies that the wall or the flow has separated from the wall and is continuing to flow in this separated region. Okay, so this is exactly how the terminology of flow separation comes into picture. Okay, okay then, so I hope I'll just go through these statements. Okay, these are quite properly understandable by themselves, so I'll just go through it, dictate it, and if you have any doubt you can just stop me and ask. Okay, so what happens beyond the separation point? Okay, so there is a low pressure region formed beyond the separation point. Because of the formation of this low pressure region, which is called the wake, the symmetry in the pressure distribution around the body is disturbed. Okay, which we didn't observe in the case of low Reynolds number flow. It was symmetric in both the sides, right? For flow over circular cylinder, we saw that the pressure distribution was uniform from the leading edge to the center, and also from the center to the trailing edge. So there was uniformity in the pressure distribution. Okay, for low Reynolds number flow, but this is not the case of low Reynolds number flow. This is the high Reynolds number flow region, right? Or the boundary layer flow regions, which is exactly the high Reynolds number flow region. So how this exactly shows how it is, because governing equations wise also it was quite different, but now qualitatively also you can see how it is different from the low Reynolds number flow regime. Okay, so now if there was no separation of the boundary layer, the pressure distribution of the about the axis would have been the same for the left and the right region of the cylinder. Okay, which is exactly in the case of low Reynolds number flow. Okay, because of the flow separation, it gives rise to a low pressure region, and the pressure distribution does not remain uniform. Okay, and therefore there occurs a net resultant force because of the pressure distribution that acts on the body. Right? Since let me just go back. Since there is a higher pressure in this region compared to this one, which basically tells there is a adverse pressure gradient. So basically there is a net imbalance of forces due to pressure. So, and this imbalance in pressure forces results in net force on the cylinder. Okay, this is what we also termed as form drag, which we will eventually see. The net force due to pressure distribution around the body cannot be neglected in the case of flow over curved surfaces. Okay, and this is what we have neglected in the case of flat plate, because the flat plate was considered to be completely horizontal, so there was no pressure gradient that acted upon the flat plate. Okay, so that's why there is no pressure term while evaluating the X momentum equation, right? It was zero in the case of flow over flat plate. The boundary okay, this is also important. Okay. The boundary layer, after coming in contact with the surface of the body, has a tendency to slow down and lose its energy. Okay, quite understandable because of viscous effects. But still, it manages to keep moving forward over the body because of two main reasons. First is that it gains energy from the outer layer by the shear interaction. That is basically the case of flow over flat plate. The incoming flow, the inertia of the incoming flow gives energy to the flow to continue to flow over the flat plate. Otherwise, it would dissipate, right? Because there is a dissipation because of viscous effects of the flow. That it will tend to slow down the flow and eventually stop the flow completely. But since the incoming flow has some energy that is being continuously supplied to make the flow move in the forward direction, so the flow continues to move forward, right? That's why it is also told to be inertia driven flow. Okay. And secondly, the presence of a favorable pressure gradient that keeps this flow moving. Okay, these are two main reasons. For dP by dx greater than 0, the pressure gradient resists the forward movement of the boundary layer. Okay. The presence of an adverse pressure gradient has a tendency of continuous reduction in the momentum that may give rise to a shift in the direction of the velocity. That is how we get a back flow or reverse flow. Okay, I hope this is quite understandable, so I won't go and again explain it thoroughly. Okay, so it is again is if dp by dx is less than 0, there will not be any boundary separation. Okay, so the existence of an adverse pressure gradient is a necessary condition for boundary separation, but not a sufficient condition. We will see why. Necessary condition in the sense that if it exists, there may be boundary separation, but it is not compulsory. But if adverse pressure gradient does not exist, there will not be any boundary separation. But it is what the meaning of an necessary condition. Okay, so that is what we explain here, that if dp by dx is less than 0, there will not be any boundary separation. Okay, very important, please note it down. So what is a sufficient condition, or why it is not a sufficient condition? Because even if dp by dx is greater than 0, the energy attained by the shear interaction or the inertia of the flow from the outer flow may be sufficient enough to overcome this resistance due to adverse pressure gradient and make the flow move continuously continuously in the forward direction. Okay, so there is a balance. Like once this inertia flow is less or is not able to overcome this adverse pressure gradient or resistance due to adverse pressure gradient, the flow will separate. Okay, okay, so this part I will just skip past a bit fast, because here they briefly discuss about resultant force and flow on immersed bodies. Okay, so there are two types. There is basically lift force and drag force, where the drag force is a resultant of the skin friction drag and the pressure drag or the form drag, as I told. Okay, so the skin friction drag is basically because of the viscous effects of the flow, so or basically because of velocity gradients, right? This is actually this existence of velocity gradients is the outcome of viscous effect. So you can tell that the skin friction effect is the outcome of the viscous effects of the flow. Okay, and this form drag is an interesting one. So form drag is specifically because of the difference in the pressures at the 2 points or two parts of the flow field. Okay, if there is a difference in pressure, which usually occurs because of the shape of the body or the flow over that particular shaped body, which results in difference in pressures, which then in turn results in a drag force, and that resultant force which can be interpreted as a drag force, or which is known as a pressure drag or form drag. Form drag, why? Because this form drag is highly dependent on the form or shape of the body. That's why it is called form drag. Okay. So let's see now. Okay. The turbulent boundary layer has a greater momentum compared to laminar boundary layer. Okay, despite average, because the net incoming velocity is higher, so momentum will be higher. Okay. And thus has a greater chance to overcome the adverse pressure gradients. Again, it's quite obvious. Thus, flow separation can be delayed by the virtue of having a turbulent boundary layer. Okay. I hope this part you understand. Okay, since the flow has higher inertia, it has a higher capability to overcome the adverse pressure gradients, and thus turbulent boundary layers tend to separate later or in a much later time compared to laminar boundary layers. Okay, and this is why you can see that there are dimples on golf balls, right? If the golf ball was completely plain, completely smooth, it will have a laminar boundary layer. Okay, so we just draw both the balls. So this is again a standard example. I hope you all know, but still it helps in understanding the concepts. So in the case of golf ball, if it is smooth, the flow tends to separate at this point. Okay, and there again the vortices and the vortex shedding takes place. This vortex shedding is also known as the von Karman vortex shedding. In the case of cylinders, it's a specific name. So these are the vortex shedding. Okay. But in the case of flow, let me just move it a bit fast. So in the case of a turbulent boundary layer, what happens is that this delay is separated. Why? Because since the flow is higher inertia, it has a tendency to delay the flow separation, or basically it has a tendency to overcome this adverse pressure gradients. or more importantly, you can also understand in a way that since there are dimples on the ball, just draw it, there are dimples on the ball. These dimples, what they do is they trigger the boundary layer to transition, to make transition to from laminar to turbulent, so that the net momentum transfer across different layers of the fluid flow is higher. And this high momentum transfer results in the flow to be attached to the surface for a quite longer time, for a comparatively longer time compared to the laminar boundary layer. Okay, so here you will observe that the boundary layer extends up to this point, in fact up to this point, and then the vortex shedding takes place, or force separation takes place. So the interesting thing is that, as you will see here, the skin friction drag is less, but pressure drag or form drag is more. Just opposite to it, here the skin friction drag is more. Why? Because the boundary layer, as I just told you, shear stress at the turbulent boundary layers are higher compared to laminar boundary layers. So skin friction drag, is more, and form drag is less. There is what being exactly explained here. The turbulent boundary layers delay separation and less form drag. Okay. So that is what is told here. For laminar boundary layers, that is in the case of a plain golf ball, there will be less skin friction drag and a greater form drag. Similarly, in the case of turbulent boundary layer, there will be more skin friction drag because of the higher velocity gradients, and a lower. Why? Because tau wall is equal to mu by dou y to the wall, and there will be less form drag. Why? Because it delays the flow separation. Right. And then finally we will discuss about. Let's just go to the statement so that it is quite perfectly clear that if the shape of a body is such that it induces early flow separation, then the form drag is dominant. Okay, and if the shape of the body is such that it delays the flow separation, then the skin friction drag is dominant. Okay, so now you tell me that it's just an exercise question, you can answer it or you can just think about it. What is the main purpose of streamlining a body? Does streamlining a body always results in lesser drag, or it has some counter effects, like streamlining a body may reduce some certain kind of drag and increase some certain kind of drag? Is it so? Like, or as engineers, do we look into an optimized way, like where both of these effects are at its minimum, or we can go on streamlining a body as much as we can so that we can reduce the drag, or is it so that it reduces the net drag? So we can think about it. It's a important or a good exercise for all the learners. Okay. So because I also didn't know about this when I first learned this during my bachelor's, so you can just go back and think about it. So the final part is, what are the possible measures to delay flow separation? First is boundary suction or boundary injection. Basically, like if you draw some pores in the surface of the body, you can either suck the air or the fluid or inject some fluid so that you can enhance the momentum transfer in the boundary layer. This is what exactly being done in the case of the dimples that exist in the golf balls. They enhance the momentum transfer so that they could energize the boundary layer so that the boundary layer do not separate easily. Okay. What you can do is streamline the body to delay the boundary layer separation, or roughening the surface artificially. This is passive flow controls. This is basically what is being done in the case of golf balls. Or you can also know this term. I know that you can. I think you may know this term, vortex generators. if you next time when you travel a plane, you just see over the wings of the aircraft. This is the wing. You will certainly see some protrusions coming out of the, sorry, this is the wing, airfoil shaped wing. So you will certainly see some protrusions that come out of its near its trailing edge or leading edge. Okay, mostly it's near its trailing edge. So these are called vortex generators. Okay. So again, it's an exercise for you. You just go through it and see how it delays flow separation. Basically, what is that? Does is that it energizes the boundary layer again, so that the flow separation can be delayed. Okay. And you can clearly now understand that the flow separation or the drag or the main purpose of designing a wing is to reduce the form drag, okay, which in adverse conditions can result in stalling of the aircraft, which is again a very adverse effect that may even result in very dangerous accidents. Okay. So this is what being done here. So okay, there's again a lot of things that to discuss in the case of airfoils, the effect of increasing the angle of attack, how it increases the lift, or how it then, but again in turn increases the form drag. So there are lots of things that can discuss, but I guess for the scope of this course, I will limit myself up to this, and I really hope that I was able to help you out in this course. Like also, I feel that there might have been some instances that I wasn't able to clarify the concepts properly. I apologize for that, but I also think that there were some concepts that I was able to give my 100% to teach you and make you understand. So I hope you were able to understand that. So okay, then I wish all of you all the best for your exams. Please go to the lectures Professor Gupta again go to the PPT material that he has provided, and also please go to the notes that both the TS, me and the other TA has provided. Go to the notes, go to the problems that you have solved. I guess that will be quite enough for your understanding. Okay, then that's all from my side. Thank you and thanks a lot. Thank you so much for being a part of this course. I hope that I'm again given an opportunity to teach in these sessions. So meet you again in the next sessions. Okay, for the next course. Okay then, thank you so much.